Hi guys, we need to do one more homework problem, or go over one of the whole problems from 3.1, and that was specifically on greedy algorithms. And I didn't assign too many homework problems, and so basically it was just going over the given homework algorithms that we have seen. To design a greedy algorithm or design an algorithm of this greedy algorithms are normally deal with more complex problems, and that's makes it harder, of course, to write them. And in another thing is that it is much more work to show that it actually is a good greedy algorithm. But greedy means to be solve it as quickly as you can by a criteria that you determine in advance. Remember, that's from the lecture, we learned that. Now, what you hope is that by doing that, you actually get the optimal solution. But we have seen that is not always the case, and also in this homework problem, we will see it one more time. So let's go to problem number 55. And so in 55, you are supposed to make change using not dollars, cents. So coins, but we not write cent here, of 25 coin, a quarter, what is it using? Dimes and pennies. And so greediness here in this our case always meant that we're going to try to pay with as big coins as possible. That's actually kind of what you're going to do if you're going to look for change. You first look for as many quarters and then say, okay, how much more do I know? Oh, okay, here's a couple of dimes. And then you go always trying to optimize it that way, but that's the greediness, but it's not always optimal. And you will see here, for instance, let's do 55A. 55A is 80 from 53, so 51 cents. 51. So this is A. How do you make 51? Greedy is you take 25 because that's the first you can pay. After that, you still can pay 25, and then you've left with one left, so you pay that. And this is clearly a good solution. There's no better solution. I'll tell you when I solve the problem at the end, actually how you can argue that there is no better solution. Well, let me say it. Look, whether I had a nickel or not, in this particular choice, I would never have chosen a nickel, right? So this is also the solution that the original problem, where using all our coins, would give me. And we know that gives the optimal. I didn't prove it, we didn't look at the proof, but in the textbook, I mentioned it also, I said this was an optimal one. But it requires a proof, and I hope for those that are interested, you looked at the proof that they gave, the argument that they gave in the textbook. Fortunately, as I said, pointed... no, sorry, I'm confused. Yes, so okay. So it is the best solution because it's the best solution given by the original one. Now, but B, here you see something else happens. I think it was 69, right? Yeah, 69. So this algorithm says, okay, 25, and then 50 is gone, so 19 is left. Okay, I can do this with a 10, and now we have only ones left, so I have a 1 plus a 1 plus a 1 plus 1, 5, 6, 7, 8, 9. This is what because I have no nickels, once I have 9 left, I have to use pennies. Now, let's see what would have, this was question number 53. 53 was the original problem, right? How would 69 have been dealt with in the original problem? It would be 25 plus 10. That leaves me with how much left? 9. Oh, I would take a dime and then I would put in 4 pennies. Okay? This is 1, 2, 3, 4, 5, 6, 7, 8 coins. How many coins do I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 coins. So these are 12 coins. And this is clearly less coins, but it's not something we can use. So I'm putting it here, but it is not a solution for us because it uses the 5 coin, it uses a nickel, which we're not allowed to. So there are better solutions, but not given, at least not the one that the previous algorithm gives will need nickel. Yet there are still better solutions. And let me show you how. 69, I can do 25 plus 1 plus 1 plus 1 plus 1. So I'm going to get already myself to the 9 here, so that I have 29, and what I need 40 more, which is 4 dimes. So I have now, so this the optimal one using the coins that we can, all our coins is 1, 2, 3, 4, 5, 6, 7, 8, right? Sorry, I forgot. So these were 8 coins. Now, how many coins do I use here? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 coins. Now, of course, it's not as good as the optimal one, because that's why it was the optimal one, right? But it is better than the greedy one. The greedy one would try to pay with as high a coin as possible, but the result is that you end with 9 cents left that you can only pay with once. If, on the other hand, you make this adjustment here, I put the ones here, you might say, that's not greedy. No, of course not. For one thing, I know it's not going to be a greedy algorithm, so I have to do something else here. Now, I could have put first the 4 tens and then the 4 ones, but the reason I put the 4 ones first is because I'm smart and I'm thinking, what is causing me problems in, why do I get so many coins in 69 is because I end up with 9 cents. But if I have 25, I can make it end in 9 by adding just more 4 pennies. And then everything else will be, what is left is a multiple of 10 that I can pay with dimes. Okay, so here we see an example that the greedy algorithm, which would give me this solution, is not optimal because this is better. Now in the next two ones, again, 76 cents, well, that is clearly 25 plus 25 plus 25 plus 1, and is also the solution that the original problem would give, and therefore we know it's optimal. And D would be 60 cents, that would be 25 plus 25 plus 10. Again, we even if I run the original algorithm where I'm allowed to use nickels, I don't need nickels for this case, and therefore the solution I get is also viable in, or is also acceptable in the current situation. Okay, that was for 55. 57. So we have all these times and we have to schedule them. I told you this, that it is perhaps nice to put this a little bit on the line, that you see a little bit visually what is happening. So they were nice for us, and they ordered the talks by putting the one with the first, the earliest ending time first. Okay, so I'm going to record all the talks. So the first talk is from 9 to 9:40. So I have, they go until what? Until, what's the last ending time? 11:50, no, 11:25. Oh, actually they didn't. Okay, so the first time is 9, I think. So I can from 9, and the last time that is recorded here, the biggest time is 11:30. I hope I didn't make mistakes, because I don't. So 11:30, and everything is with 15. No, yeah. So there's a lot of times that I have to put here. 11:30. So 9. I see. So 9. So this would be, that's 5, 10, 15, 20, 25, 30. So this is 9:30. 35, 40, 45, perhaps 9:45 here, 50, 55, this would be then 10 o'clock, 5, 10, 15, perhaps 10:15, I'd write it down, 20, 25, 30, so this would be 10:30, 35, 40, 45, then 45, 50, 55, and this would be 11 o'clock. I'm just getting 5, 10, 15, so this is 11:15, 20, 25, 30. Okay, So the first talk was from 9 to 9:45. So from 9 to 9:45. This was talk 1. I'm just going to put a 1 here. The next one was from 9:30 to 10. So this was here to there. That's talk 2. The next one was from 9:50 to 10:15. 9:50. So from here until, okay, I'm gonna have to keep my hand here, otherwise I'm gonna read this wrong. To 10:15. So that was a very this talk 10:15. That was number talk 3. Talk 4 from 10 to 10:30. From 10 to 10:30. So you see, although it's a bit tedious, right? The algorithm doesn't draw anything. But for us to understand and work it out, it's much easier to draw it. It takes time to draw it. But once it's drawn, it makes it easier for us to operate it. So, okay, I shouldn't have talked, but now I lost my train of... Okay, from 10:10 to 10:25. So from 10:10 to 10:25, that's a very short talk. That's talk 5. And then from 10:30 to 10:55, 10:30 to 10:55. Okay, I'm gonna have to, I should have put on checkered thing. Now checkered's not gonna, a little bit go down here that it's clear what my times are. So this was talk 6. Okay, this was 10:32 to 10:55, 10:30 to 10:15 to 10:45, 10:15. So this is start here to 10:45, which would be here. That's talk 7. Okay, then 10:30 to 11, 10:30 to 11. Let's start number 8, 10:30 to 11, 10:45 to 11:30, 10:45. So this is 10:45. Was this also 10:45 to the 7? Yeah, I think so, right? Okay, 10:45. So this should be at the same height here. Time 9, and this goes from 10:45 to 11:30. Now, of course, if I'm going to make a mistake here, then I'm going to get the wrong answer, right? So I hope I'm drawing everything correct here, and if not, then do it with what I draw and forget what the text, what the question, the original question was. 10:55 to 11:25. 10:55. Was also 10:55, guy. Okay, this has to go. Perhaps make a little bit more space here. So 10:55, so this is 10:55, this is where talk 10 starts and it ends at 11:25. This is 11:25. Talk 10, this was at 11:30. And then finally from 11 to 11:15, that's a very short talk. That is from here to here, that's talk 11. Let's see, there were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, seems I got them all. So I want to point out that the algorithm that I gave you is different from the textbook, because the textbook, I think, makes mistakes there. There's something very weird that they do. So this is a much nicer algorithm. So the algorithm of schedule, so this was called, so sorry, I should call it procedure, right? I'm just going to copy it again what it was, okay? So procedure is schedule. I'm going to use caps here, otherwise it might be illegible. And so we have a list of talks. And this is the list of talks. And as I said, in the textbook they make a big deal about ordering these things, but that's actually all not necessary. So, okay, they are ordered somehow a little bit of starting times, or I think they seem to be listed at increasing. No, there is no actual order either. There's just a bunch of talks here. So this is L. So L consists of these 11 talks. Of course, every talk is basically determined by its starting time and its ending time. Okay, so that's the schedule of L. That's the input. L is a. I'm not going to write it anymore. And so but how did it work? The schedule will be, the talks that we schedule will come into S. S will capture all the talks that we can schedule. And so we do a while loop. I'm not going to explain anymore why we do this. This is the thing explained in the lecture last time. While the list is not empty, then what do? Well, we choose a talk in our list with earliest ending time. And that one we're going to schedule. So we add that to our schedule. Okay. So once we choose this, and there's always one, of course, unless because it's not empty. There's always one with the earliest ending time, and it could be several with the earliest ending time, and then I pick one. Okay. The first one I encounter, I pick that. Of course, I agree that to choose the one with earliest ending time, that in itself is a search for a kind of a minimum. But we have seen how we do this, and so we can write this phrase here, thinking of it as a command that is already implemented. Okay, so as I said, we add this to the schedule, and then, and this is important, now we remove all talks incompatible with this talk I. So I is a talk, and what I mean I is a talk, it really is a pair of two numbers, the beginning time and end time. Okay, but it doesn't matter. I just call I the talk. So I remove all talks that are incompatible with I, that overlap with I, from remove them from L. And that, of course, is how L changes, and that's why at some point this will be empty. And then once I'm finished, we know we can write return here. We return L, because that will be the list of all talks that I can schedule, and that is, we haven't proven it, but we stated it that this is optimal. So this always will be the longest possible list. In Discrete Math 2, we will discuss how other criteria, you might not want to do the most, but you can do, it can be that you get price, that they cost, there's a cost to scheduling certain things, and that you want to optimize the cost or something else. Okay, that's it. Okay, so let's do this. And so in the beginning, so we're gonna write down our procedure, and we're gonna build S as we go along. Okay, and I'll do this here on top. I'm gonna get a little bit of space here. And so S, so originally S is empty, and this is gonna keep changing, right? And each time I get a new S, I'll write it down. Okay, what I'll do, well, L is not empty, so S is empty, okay. While L is not empty, we choose the I with the earliest end time. And the one with the earliest end time is, so we see the earliest end time is this end time, right? So we're gonna put 1 in our guy. So S, so L is everything else. So L is talk 1 up to 11, and S, in the next step, S consists now of talk 1. But now we have to delete from L all the talks that are incompatible with 1. In particular, we have to remove 1 itself. So we're gonna do this by scratching it out, right? So N has to go, and 2 also has to go, but it overlaps. But that's it. Okay, good. So we can move on. So we have now 3, 4, all the way up to 11. Okay, so what happens next? So we have 1, we're going to add the next one. Which we're going to add? The one with the earliest end time. The earliest end time that I see is this one. Oh, no, that's gone. Sorry, that's gone. So, yeah, I'm going to make them really gone. Is that okay with you guys? They're gone, right? Okay, they're gone. I have to make this a little bit smaller, because otherwise I'm going to erase too much. Okay. So the earliest end time that is now available seems to be this end time, and this comes from talk 3. Okay, so I'm gonna add 3 to the whole thing. Okay, 3, but it means that I'm also gonna have to revise my list by removing at least 3. So I'm gonna remove 3. Okay, let's do it. I hope that this not gets too much. Okay, 3 is gone. Oh no, I shouldn't. I should be careful with that. Oh, sorry, I'm going to do 3 the last because I have to see what conflicts with 3. 4 and 5 conflict with 3. 7 doesn't, because remember a next talk can start exactly at the same time as the previous talk ends. It would be a logistic disaster, but that's not something we concern ourselves with. So 5 and 4 are gone, and therefore also 3 is gone. So we have left 6, 7, 8, 9. Okay, 6, 7, all the way up to 11 is still left. Okay, we move on. The next one. What is of the remaining one has now the 3 is gone too. I forgot to get it with. So what is now still left? Earliest end time seems to be 7, right? Everybody sees it? Okay, 7. Okay, 7. So what is now incompatible with 7? Well, 6 and 8 are incompatible, so let's get rid of those already. 6 is incompatible, 8 is incompatible. 9 is not because it ends in 10 and 11. Okay, so we have 8, 9, 10 and 11. L is 8, 9, 10 and 11. Oh, 7 also has to go. I keep forgetting to do my thing itself. Okay, so what's now the earliest end time? Let's see. This one, oh, it's actually this one, 11. Okay, I'm going to put 11 there. Hello, 11, welcome. And then now I have to get everything that is incompatible with 11. Wait, 8, why is 8 gone? Oh, 8 is gone, sorry, 8 was gone. I put it there, but it should have gone. So 9, 10, 11, and so, right, 9 and 10 are all incompatible, and so of course is 11. So at this point, L is empty. Okay, L is empty, and therefore the process stops, and the output is this. And this is the best I can do. That's the optimal part. Okay, so then I also gave you one optional problem. I want to go over it a little bit quick, not spending too much time because it was optional, but it's good to, I hope some of you tried it. It's a good challenge. It has a star, and a star also means, oh, that's not easy. Okay, so let's see who was courageous enough to do this. Devise a greedy algorithm that determines the fewest lecture halls needed to accommodate n talks given the starting and ending time for each talk. So same problem about the talks, but now we need to schedule all of them, but we want to do with as many auditoria, with as least number of auditoria as possible. Now there are several. The greedy part. What is greedy is, I find it sometimes a little bit debatable what actually is greedy. So I'm going to propose 2 solutions. They are different, and I'll leave it up to you to see what you think is the most greedy. So let's call one procedure. And to practice something else, I'm going to kind of write down the procedure, okay? And then see what you can figure out what my procedure is doing. I'll give comments about it. So I call it Hall schedule. And the input is again a list of talks. You can think of this as the previous list here, okay? And we can run it on this previous list. Unfortunately, I erased so much that I don't feel like going, oh, actually, it shouldn't be that hard, right? So this is that, this is that, this is that. No, it's not that bad. So perhaps we can try it on this guy. Okay, so Hall schedule. And this is an interesting problem, right? Because, okay, this scheduling, you kind of might already see it a little bit. You might eyeball it and say, oh, I see a solution. But how many halls you need? That's not so clear to see anymore. So cannot guess it actually, right? Is it going to be 2 or is it going to be 7? God knows, right? It could be as much as 11, right? If all these talks have 5 minutes, the same 5 minutes overlap, well, they all have to be scheduled in different hall. So this is very well possible. Of course, the number of halls can never be more than the number of talks. But so what I'm saying is the following: the number of halls, I'm gonna call that halls. Okay, and of course, I'm optimistic and say I don't need any halls, but that only is going to work if I not need to schedule any talks, right? And so what I'm going to do, I'm going to use my previous scheduling. I'm going to say, okay, I'm going to try to schedule as many talks as possible in my first hall. After all, that was an optimal strategy, right? I knew it was optimal, so I'm going to run the previous procedure on my list, and I put those in hall 1. Okay, so but it means I'm okay. The question is, what do you want this algorithm to output? Now I'm going to be taking the easy way out, and I'm going to say, well, you asked me how many, and I'm going to answer you how many, but I'm not going to tell you how you have to do it. Of course, that's really what you want. It's a good exercise, and I challenge you to do it. Given the algorithm that I'm going to give, modify it a little bit to keep track of how to schedule it in the various halls. But I'm not going to really think about that. Okay, so here's what I'm doing. I'm thinking, okay, again, what I will do is my list, I'm going to start removing talks. Whenever I schedule a talk, I'm going to remove it, right? And I don't need to deal with that. So while, that's going to be a while. That should not be in a regular in regular thing, right? So that could be a while my list is not empty. What I'm going to do? Well, let's schedule. The previous procedure was called schedule, right? So apply schedule to your L, and the result was S was a bunch of talks from that schedule. If you really, really lucky, it was all the talks, but most likely it's not. Okay. So what you do now next? You remove these talks, right? Remove these talks. Sorry. Yeah, this is going to make something I keep doing because I find writing a minus sign between two sets a bit weird. But okay. So remember, this is the difference, right? This is the set that you obtain by deleting the talks from S from L. So whatever remains. That's my new L. But of course, I have used a hull, so I'm going to increase the hulls. Sorry, let me write this again. So the counter of many hulls I use has to be increased by 1 because I did use a hull. Right? So the idea is I am filling up my hulls, and as I go along, each time when I run this guy, on whatever is left, I'm putting these in the next available hull, and then I'm telling me, okay, I have used now one more hull. Now, if this is empty, everything is scheduled, and therefore this loop stops, and I'm done. And hull will be the exact amount of hulls that I use. So this is very short algorithm says return hull. This will tell you how many hulls we use. Let's run it on our guy here. So, well, that's going to be a little bit time consuming, right? Because, okay, we run it the first time and we know we use 1, 3, 7, 11. So those go in hull 1. Okay? Remember I told you the challenge was to modify this algorithm to keep track of what schedules are which talks are scheduled in which hulls. This one, my procedure doesn't do this, right? My procedure just says how many hulls there are. So how many times I have to repeat this thing. Okay, so in this, recording this thing, 1, 3, 7, and 11 have been scheduled. And now I have to, where 1? I didn't do 1. 1, 3, 7, 11 gone. And now I have to repeat. Now, I don't want to do this because, okay, well, let me do it. See what I can do it quickly. Okay, let's go for a bit. I have nothing else to do. It's you see it's almost midnight. If you see my time up left side up there. So let's for the fun let's do it. Okay, so. Again, I start with now I'm running the original this algorithm, right? So I start with an empty schedule, and my list consists of 2, 4, 5, 6, 8, 9, and 10. Okay, so I'm going to increase S, but I'm going to scratch out things in L. I'm not going to rewrite L anytime. So the first one I can schedule seems to be 2, right? Okay, so I schedule 2, and therefore 2 goes. And is there anything that is incompatible with 2? No, actually that's the only thing I have to scratch out. Okay, so 2 is gone. It's now a part of my talk. Next one. Okay, so after 2 is gone, yeah, 2 is scheduled, so I'm actually going to erase it. I have to be a little bit careful what I'm going to erase and not erase here, because otherwise I'll get completely lost. So what is now the next earliest time? That is talk 5. So that is the next one I'm going to put in here. So, okay. So I'm going to write S here. I'm building S like that, right? All the ones. I had 2 in there. Now so this is S. Sorry. Let me rewrite it because it's too sloppy. So here is S is going to be, and I'm going to write it in a column. No, I can write it here, right? I can write it, right. So 2 is in there now. Okay. So the next one I said was 5, right? So 5 will go out there, but incompatible with 5 is also 4. So I have to get rid of 4. So 5 is gone, so I'm going to erase 5 here, but I'm going to leave 4 in because I have to later deal with 4. Okay. But as far as I'm concerned, I cannot use it anymore in this run of this program. So what is the next? The earliest end time seems to be 6. Am I right? Yeah, 6. So 6. So 6 will be gone. Let's take it out. Oh no, I have to see what is incompatible with 6. 8 and 9 are incompatible with 6. So this is, oops, 6 and 8 and 9 are also incompatible. Okay, so but 6 has to be gone because 6 is now scheduled. Remember, this is the part here. So, right, I'm always... no, sorry. Yeah, this is what I'm doing here, right? Oh, yeah, sorry. Okay. What am I doing? Okay, so what's left are these 3 talks, right? Oh, no, there's only 10. And what happened to 11? Oh, 11 was already gone. Only 10 is left, so that's it. I'm not going to think anymore. I'm not going to think anymore, just 10. Okay, so the next hall will have 2, 5, 6, and 10 in there. So 10 is gone also. And so I'm actually left with 4, 8, and 9. Okay, so this is now my new procedure. Sorry, they're both procedures, but this is the procedure what have I done? I just completed this guy for the second time. And the schedule that I got from the second time, that means that these go in second hall, 2, 5, 6, and 10. I'm going to now remove them. Okay, so what is my new list? What is my list that remains? Now, okay, one thing. This procedure uses L and S as variables. This uses L and S as variables. Now, we can discuss this. We're not implementing this, and so the idea is that variables in one program can be redefined, but they're always what we call local. They change only inside the program, right? So if I'm using an L outside, so this L here, this outside L, is also used as a variable here, and it gets changed inside here. But once this procedure is run, it goes back to what original L was. That's the assumption I make. It's not specified in the textbook what you should do or not, but I'm assuming that this is good practice again in programming. So okay, so what we are left with, as I said, we have now S. What is left is 4, 8, and 9. 4, 8, and 9. So sorry, L. The actual list, right? So right. So, yes. So I scheduled hall 2, removed them from hall 2, and increased the hall. Now, at the point that I was doing hall was 1, but now I'm saying, okay, now hall has become 2. So hall is now 2, okay? L is still not empty, so I'm going to do it again. Okay, so what can we schedule here? This is going to go much faster, right? So again, I'm running now the schedule algorithm, the algorithm that we discussed in the textbook. Okay, so I'm running that. What's the earliest start time? That's 4. So 4 will be scheduled, so 4 can go. And is anything conflicting with 4? Well, the 2 that I have to look at is 8 and 9. They're not conflicting, so fine, that's great. And then the earliest end time is 8. So 8 is also scheduled. but 9 is conflicting with it. Oh, sorry, should have waited to do that. First, I have to see that 9 is conflicting with it, so I have to already. So okay, 4 was gone. 9 has to be taken out as well. 8 has to be taken out, so it's empty here. That means this is the end of my scheduling. So I have now also scheduled talk 8. So again, this means I concluded this one for the third time, and I found these 2 talks. Remember, if you want to implement this, keeping track of it, then you have to do this at this point. I remove them, and I say, okay, this was now 3 halls. But unfortunately, it's still not empty, and you'll see now, of course, there's 1 talk left, there will be a 4th hall. Okay, so this is my greedy algorithm, but I want to give you another one. Actually, that's the one that they propose in the textbook. I'm going to go over it very quickly because I don't want to waste too much time here. So same procedure, let me call it something else. So procedure TB hall schedule, textbook hall schedule, because that's the one in the back of the book that they at the end of the solution. So again, a list L. Now they describe it, and I'm going to actually write the pseudocode for it because I think it's actually nicer. Well, what do I have to do here? I have to keep again track of the number of halls, right? Right. So the number of halls is going to be again the same thing. So halls originally is going to be 0, but actually this one actually will tell me what is in each hall. So it already takes care of the thing that I asked you to do in the previous one, but you see it's a little bit tedious, more tedious. So what I do is, while, same thing, again I'm going to take my original L, I'm going to start removing things for it, but so in other words, I keep doing it until I have nothing to schedule left anymore. Yeah. So, and now comes a bit the tricky part. I'm going to run over all halls that I have at the moment used. But at the moment I have not used any hall. Okay? So what I'm going to say is while, so this is a second while J, okay, I have to say J is 1. Sorry. This is a little bit when you have counters that you're going to use in a while, you have to first declare them. Sorry, so I have to do this. So declare the counter J to be 1, and then while this counter J is smaller than the number of halls that I have already used, I'm going to try to fit, so what is the idea here? I'm going to put 1 talk at a time, and I'm going to put them in whichever hall I can. I'm going to try to put them only in the first hall, but if I cannot do it, then I put it in the second hall. If I cannot do it, I put it in the third hall. And if I cannot put anything in all the halls that I have already used, then I open up a new hall. Okay? So while J is less than the number of halls, so while I'm going, J will loop through, it starts with the first hall and will end on the 0 and on the last hall. Now, if the halls are 0, if in the original, let's see, I will discuss what happens in the original run of this thing. So, but let me write down the juice of the thing. So while I'm doing this, I'm going to do a comparison. What I'm going to say is, if I need a bit more space. So let me try. If talk I, remember, okay, sorry, I forgot to do one thing more. I'm also going to take the so I'm trying to put all the talks in my halls, and I'm going to do this. I'm not going to do by the first talk, the second talk, the third. I'm going to try to put the talk with the smallest end time, the earliest end time. I'm going to try to schedule that first, because that also was a good strategy in the original problem, right? In this original problem, I always tried to put the one with the earliest ending time. Now, instead of trying to put it in this one hall, I'm going to put it in whatever hall I can, starting with hall 1. If that doesn't go, and go to hall 2. Okay, so I is going to be the talk with the earliest So I is, sorry, let me write it, I'm sorry, it's a little bit small here. Let me write this, make this a little bit smaller. So if L is not empty, let I be the talk with the earliest end time. And that talk I'm going to try to schedule, sorry, I should have said that, and I'm going to try to schedule it in one of the halls that I have already, and if not, then I make a new hall. So while I'm going to the hall, so J will walk to the halls. You can think of it really, right? I'm going to look at each hall and say, has this space, do I still have space? So if talk I, if that talk, so if I, so we don't know that's a talk. So if I is compatible with HI. Now what is HI? I haven't really said what HI is, but you'll see I will define it. These are going to be the talks scheduled in the ith hall. Okay? They have not appeared yet, but I'm already using it. It's a bit weird, of course, so I have to say so I have to, this initialization is sometimes a little bit an issue where I'm going to do this. So let's call H1 to be empty. At the moment I'm going to introduce H1 already and make it empty. So if I is compatible with HI, of course in the first round, since H1 is empty, it is compatible with that. If I is compatible with HI, what do I do then? Then I'm going to add it to this schedule. Oh, sorry, I hope, sorry, not I said the J counts the halls I'm walking to. So if talk I, which was the talk with the earliest end time. So in our example, this was talk 1, okay? If talk 1 is compatible, but let's say we're somewhere of already scheduled talks by the earliest end time, we go to the point of earliest end time. Suppose it's the time is, we have to schedule, we have already scheduled these talks, they are gone. Let's say 5 is gone as well, so 5 and 4 are gone. So we have to now talk whatever is left here. Okay, I take the one with the earliest end time. In this case, that would be 7. I take that talk, and I'm going to try to put it in whatever hall I can. If so, J, I'm going to go, J is 1. I start with J is for the first hall. So J is my first hall. Is this talk compatible with the talks that are in hall 1? If so, if it's compatible, then I'm going to add it. So then, sorry, I'm going to then, and then what do? Then I add it. So then Hj will become Hj union I. I add I to it. Okay. And of course, I have now scheduled I, so I'm going to remove it. There's no, I shouldn't try to put it somewhere else anymore. It has been put now. We're only going to schedule it once, right? That's what I do if it works. If it's not, what should I do if it doesn't work? I should go to the next hall, right? So else, so here you see an else. Else, I'm going to go to the next hall. What does that mean? Well, increase your J. J is counting which hall you're in, right? So increase J, and so else J becomes J plus 1. Now, what can happen? Two things can happen. Either this all works out with whichever number of halls I had, but it could be that I have gone through this whole thing. I tried all the halls, and never was I able to put I inside one of the halls because it was never compatible. How would I know after this has been carried out, after the while loop is carried out? Well, how do I know that I was not able to schedule I if it's still in the list? Because if it's not in the list, it's because I scheduled it. So at this point, I have to now test. So not that while loop. Sorry, it's a bit late. That's why I keep making small little mistakes like that. So we are looking here. This while loop is finished here. And so here now, just wonder, the red just means that it is aligned, right? So now I'm going to do a test. If I is still in my list, then it means I need one more hall. right? That's what it means. Then, so I'm gonna increase the number of halls. So halls will be halls plus 1. And I should introduce this new hall, this new hall. So remember, halls is the number of halls, so it's a counter that counts which hall you're in. So h of halls, that is now the new hall, right? Because I've already changed my counter. So h of halls, okay, sorry, it's a bit weird that I have this index called halls, right? But h of halls, this list here, is the new hall, and I know that I have to put I in there. So this is what's happening here. So I put I in there, and nothing else yet. This is because it's the first time I use this hall. Okay, and that's the end of the story, because after what is happening now, if this all carried out, then I'm done, right? If this while loop is carried out now, if this big while loop, the outer while loop is carried out, this means that L is empty. In other words, it means everything is scheduled, and at that point I will know exactly what the halls are, how many halls there are, because that will be being told at the end. If everything is done here, at this end, halls will be exactly the number of halls, and in fact, each of the hj will contain the talks we need. So this is a way of keeping track of the talks as well. Okay, and I'll leave it up to you to think what you prefer, what you think is the more optimal one, are they both greedy? As I said, it's sometimes a little bit up to discussion, so I don't want to go too much into it. After all, it was an optional problem, right? And we spent most of the time on it. Okay.